Today in physics, we're talking about work and power in a system that's rotating. A lot of the information in this set of notes is going to be helpful and important to you as you work on your mousetrap car and are asked to calculate work and power and horsepower for your mousetrap car as it goes down the hallway. So let's take a look. Now the first couple of slides are an example of the previous lesson, so I'm actually not going to go over those, but you can actually follow through step by step. This is asking for an acceleration of a system using something kind of similar to an Atwood machine. This is a pulley and a couple of masses. But the thing I want to show you on this next slide is that this is a little bit overwhelming to take a look at the work here, because what we've done is we've done step by step by step. What do you know and what do you need to know? And in this work, in going about solving this, we come up with that same problem where we have a system of equations with 4 equations and 4 unknowns, and so you start setting one thing equal to another. The other thing that I want to point out to you is that you'll see this z dimension on many of these equations. And remember, as things move and rotate, we're looking at the direction of a torque or the direction of an acceleration in a z dimension. And so remember, we can talk about things being positive or negative, clockwise or counterclockwise, positive x or negative x, and in this case a negative z, and so that's either going to be into the board or out of the board. Anyway, so let's talk about work. Remember, work is a scalar quantity very closely related to energy, and work is simply force times distance, but we needed to make sure that the force and the distance were in the same plane, same direction. So work is force times distance. We would say it's a dot product. Previously, we had been using x for displacement. They're using delta r for a translational system. To get into a rotating system of work, we substitute torque for force, and we're going to substitute the angle, theta, for r, and we end up with work, rotational work, is torque times theta. Torque times theta. Remember that different kinds of work are going to change different kinds of energy, but if we take a look at the net work done on your car, we're looking at its change in kinetic energy. So the net work will equal a change in kinetic energy. And then closely related to work, of course, is power. Power is the rate that you do work, if you recall. So how quickly we can do work, or work divided by time. But because work divided by time is also force times distance divided by time, and distance divided by time is velocity, we have an equation for linear work or power where we can consider power to be force times velocity. Once again, also a dot product, which means that power is a scalar quantity, even though force and velocity are vectors. To make it a vector quantity, we have to use a cross product. So we're going to substitute torque for force, and for velocity, we're going to substitute angular velocity, omega, and we end up with power is torque times omega. Power, rotational power, is torque times angular velocity, omega. Now the units for work are still joules, and the units for power are still watts, but we also have another unit for power, of course. We have horsepower. Okay, so let's talk a little bit about conservation of energy. You remember the total energy in a system, if the system is closed, remains constant. That's one of the big laws in physics. Well, our total energy is going to be the sum of our potential energy plus our kinetic energy. And we have a couple of different kinds of potential energy, and we'll have a couple of different kinds of kinetic energy, with linear kinetic energy and rotational kinetic energy. But this total is going to stay constant whether we're in a rotating system or a system that's moving in a straight line. So for gravitational systems, and you're talking about gravitational potential energy, for something that's rotating, we want to consider just the center of mass of that object and its change in height. So we'll use the center of mass. Remember, we found how to calculate, or how to find the center of mass of an object. We want to use rotational and or translational kinetic energy wherever necessary. So if we have an object that's simply rotating, we'll use rotational kinetic energy. But if the whole thing is moving and spinning, like if you throw a baseball through the air and it's moving from first base to second base, but it's also rotating, or you have a car going down the hallway that is moving translationally but also rotating, then we're going to use both kinds of kinetic energy. So here's an example problem. Rotating flywheel, which we talked about is just a big disc, provides power to a machine. The flywheel is originally rotating at 2,500 RPMs. The flywheel is a solid cylinder of mass 1,250 kilograms, so very heavy, and a diameter of 0.75 meters. If the machine requires an average power of 12 kilowatts, pay attention to kilowatts, not just watts, for how long can the flywheel provide power? So we're looking for time. The moment of inertia of a wheel is 1/2 mr squared. So they've given us the rotational inertia I of the wheel, and we're trying to find time. So as we look through this, we know we're looking for time. Inertia is 1/2 mr squared. We've got the mass of the wheel, the omega, which we need to convert. The diameter was 0.75 meters, so we know the radius is half of that. Power is 12,000 watts. We said it was 12 kilowatts. Power can be calculated as torque times omega, and because it's a dot product, we need these things to be going in the same direction. So it's torque times omega times the cosine of 180. Why that? Because this thing is slowing down. This speed is going to change. It's going to get slower and slower and slower. We've converted our omega to radians per second, and now we go about doing the work. So power is torque times omega. Now, because this omega is changing, this is going to be the average angular velocity, right? It's going to start off at 268.1 radians per second, but it's going to end up at 0. So we're going to consider this omega to be the average angular velocity. Torque is I times alpha, which we learned previously. So power is I alpha times omega. Our negative sign because of the cosine 180, right? I is 1/2 mr squared. So 1/2 mr squared times alpha times omega. And now we're looking for alpha. So we can rearrange this equation, power divided by negative 1/2 mr squared times omega. And now we begin to just plug in the variables that we have. So 12,000 watts divided by half of the mass is 625 kilograms times the radius squared times omega squared, and we factored that half to omega also, the average, right? And then we get the alpha to be negative 1.04 radians per second squared. And remember, that hasn't solved our question because we're still looking for time. So remember that time is found in the change in omega over alpha equation. So we can then rearrange initial and final angular velocities plus acceleration times time, rearrange to solve for time, and we get the time to be 251 seconds. Now that's not a very, that's a fine, appropriate unit for this to be in. That's not very helpful explanation for somebody who says, when's my power going to be off or on or whatever. If you tell them 251 seconds, they might want to just slap you. But if you tell them, 4 minutes, then they're like, oh, okay, I understand what that is, right? All right. So this last question here has a rod, a uniform mass rod, mass M, length L. It's one of those questions where we don't have numbers, we have variables again. It's going to say that it rotates around a pin through one end. So we're hinged over there on the left-hand side. We have the rod, and it's just going to be released and swing through. So it says, what is the angular speed when it reaches the lowest point? And what is the linear speed of the lowest point of the rod at this position? And then the rotational inertia of the rod is 1/3 ml squared. So remember, this can be treated very much by conservation of energy like we've done with some of the other things. Up at the top, I have potential energy. Down at the bottom, when it swings through, I have kinetic energy. And that's the strategy that I want to use. So we know that we're looking for omega. Our original angular velocity is 0. The force that's going to pull on this is mass times gravity. But remember, that's going to act at the center of mass. The radius on this, because force times radius is torque, and that's what's going to cause this rotation. The radius of this is L over 2. If the full length is L, then the radius is L over 2. The mass is big M. The inertia is 1/3 ml squared. Potential energy is mass times gravity times height. Kinetic energy is 1/2 I omega squared, because this is simply going to rotate. And net work is change in kinetic energy. And we know the work done on the center of mass will equal the change in potential energy. So as this swings through, that center of mass is high, and it's going to end up at its lowest point when it becomes vertical. So that change in height is our change in kinetic energy, and that is the work done on the center of mass. All right, so let's figure this out. So the net work done on the system will be the work done by the center of mass. The change in kinetic energy has to be equal to the loss, or the gain in kinetic energy is going to be equal to the loss in potential energy. So the change in kinetic is the change in potential, but we've put this negative sign in front of the potential because we know we're going to lose potential and gain kinetic. So change in kinetic energy is final minus initial. That's equal to negative final minus initial on the potential energy. If you factor the negative sign to both of these, you get K final minus K initial equals U initial minus U final. Certainly K initial is 0. U final is going to be 0, so then we can say the final kinetic energy is equal to the initial potential energy. Feels like we shouldn't have had to go through that. That's kind of an assumption that we could have made because we're saying the total energy at the top has to equal the total energy at the bottom. But this is just kind of proving that we can make that statement. All right, so final kinetic energy is all rotational, so it's going to be 1/2 I omega squared. Potential energy is mass times gravity times height, so let's begin substituting here. I, remember, is 1/3 ml squared. So we got 1/2 times 1/3 ml squared times omega squared. You can see we're going to have to multiply these fractions. And that's going to equal mass times gravity times height. When this swings down, that height is L over 2. Because right now, when it's in this horizontal position, as it swings down vertically, the change in height will be half of the length. So we multiply 1/3 times 1/2 and we get 1/6 ml squared times omega squared equals mg L over 2. Now we're going to try to simplify some things. You can see we've got mass on both sides and length on both sides, and then we're looking for omega. So we rearrange and solve. Omega squared is 6 mgl over 2 ml squared, and then this becomes the square root of 3g over L. That is the angular speed at the lowest point of the rod. Then it asks for the linear speed at the lowest point of the rod. Okay, so remember that we can get from linear speed, or V is linear speed, and V is R times omega. So if we're trying to solve for V, we simply need to multiply this by the radius. Well, the radius was L over 2. So square root of 3g L over L times L over 2 gives us a velocity of the square root of 3g L divided by 4. And that's as far as we can go. If we were given the length, we know gravity, we could actually come up with a number for this. Okay. This is a picture of a display of horsepower and torque. This was actually dynoing a car. A Cadillac CTS was customized for somebody. And what I want you to see from this, there's an article on it you can read about, but there's a couple of things that I want for you to be able to see. Our cars, our normal cars, do not have near the horsepower that this car has because this engine has been customized heavily. But the maximum horsepower that this achieved and the torque and some of those things are given to you here. It says that the maximum horsepower this got was 1,309 horsepower. Now, to dyno a car means you put it on a bed that has these rollers on it so that the car doesn't go anywhere, and we can engage the drive shaft and the wheels can spin and we can rev up that engine and get that highest rate. You're going to be doing the same thing to your mousetrap car on our rotational motion sensors in the lab. And you're going to take your mousetrap car and load it up and set your wheel on this little rotational wheel and allow the lever to pull a tire and spin it, and you're going to get a graph of angular velocity and time, and we'll look at your acceleration, and we know that we can use, we just said power is torque times omega. So if we know what the torque is and we know what that maximum velocity is, we can calculate your rotational power. So we're going to do something very similar to this for your car. Certainly we won't get 1,309 horsepower out of it, but if we do, I bet there's some really important people that might want to have a conversation with you. All right. So we said that power was in watts, but we also know that power is in horsepower. So rotational power is torque times omega, And remember, torque is I times alpha. So that becomes power is I alpha times omega. And alpha and omega are going to be in the same direction because we're increasing our angular velocity. Power is in watts, and we can convert to horsepower knowing that 1 horsepower is 746 watts. So rotational power divided by 746 is I times alpha times omega divided by 746, and this will give us horsepower. Knowing this helps us to calculate the horsepower of your mousetrap car also, which I think will be a fun thing for you to see. And that is all we have for today.